Okay, so we talked about some different environments. We really kind of focused sort of the last few minutes on slides 18, 19, 20 perhaps. So we're talking about how sedimentary rocks change over time and how that's a very cool story here in Kentucky and gets way more complicated elsewhere. I want to back up then to some earlier slides. We were talking about textural maturity of a sediment and the turbulence, the different water energies indicated often by grain size of siliciclastic sediments. And as we're getting back into siliciclastic sediments, we talked about texture, how that can change, thinking about the sediment weathering down from a mountain belt, like a big rock tumbler. The grains are becoming smaller, they're becoming abraded and so more rounded, and the whole sediment as a whole thing is becoming better and better sorted in that they're becoming more similar in their size. But I think the best part of the story and where it gets really exciting for me is as we're looking at how the minerals change over time. We mentioned a few minerals change. Ferromagnesian minerals, our iron, the mafic minerals that make up things like basalt, they rust because they contain a lot of iron. Feldspars undergo hydrolysis because that's very complicated. You don't have to worry about it. I don't really understand it either. But that's what happens to granite. So as we're starting out with a different rock, a mountain made of granite versus a mountain made of basalt, we're going to get very different results. And so let's get away from texture a little bit and talk back about the minerals. So I want to start out with this guy. This is one that we're familiar with from a few weeks ago. This is a basalt that actually has a lot of olivine in it too. So we have basically kind of blobs of peridotite torn from the mantle that are embedded in this mafic lava flow during a volcanic eruption. Very cool stuff, lots of iron. And that iron is going to rust. So if a rock like this, a rock that contains a lot of mafic or iron-rich ferromagnesian minerals, is exposed to the surface, it's going to get rained on, it's going to rust, it's not going to be very resistant to erosion. So we don't have a lot of sand made out of basalt because as it gets smaller and smaller, as it's broken up smaller and smaller, it's more and more likely then to chemically degrade, and we're not going to see it. There are a few places though where there are black sand beaches, and an example is the state of Hawaii, where we are creating black sediment from the weathering of those basaltic shield volcanoes that make up the Hawaiian Islands. So we can get black sand and even a couple green sand beaches of olivine. Very unusual stuff, and there's not many places in the world where we see that, but Hawaii does have some nice black sand beaches. So this indicates to us, when we find black sand beaches, it tells us that we're not very far from our source, because those black mafic minerals should not exist if there was a whole lot of transportation and a whole lot of opportunity for chemical weathering. They would be rusted away, and they do in other places. But where you have a huge source of that black sand from the volcano right there, you end up with black sand beaches. A few other special places. These are all some places I've been on vacation and enjoy collecting sand. This is an unusual sand I was not expecting. This is from Connecticut. And this sand, okay, now we're looking at some much more resistant minerals. This sand is red. It's not rust. You're not really seeing that. This is actually a highly resistant mineral to weathering. These are garnets. So this is a garnet-rich sand, which is very cool, and tells us, think about what rock, you may not know yet because it's a rock type that we'll deal with later. Garnets form generally in metamorphic rocks. So that means our source is a big body of metamorphic rocks somewhere. Like, we have some mountains in New England, and that's the source of this garnet-rich sand. Now this does indicate we're pretty far from the source, because garnets are also very, very resistant to chemical weathering, and that's pretty much all we're left with. There's not much else here but garnet. So we basically have one mineral, and it's making up this sand. So we could be very far away from the source. Another example of being very far from the source is a sand made up of almost nothing but quartz. So we see this in North Carolina, and most of your nice honey-colored or tan sand beaches are like this. They're grains of quartz, kind of like a tan color, highly, highly resistant to erosion. So our source Could be a lot of things. It could be granite, not to be mistaken with garnet, right? Very different things, and that's kind of tricky. But it could be from a granite source, because granite, like my big, nice pegmatite granite that we were checking out a couple weeks ago, has a lot of feldspar, has a lot of mica. These things can chemically weather away, and what we're left behind with is, oh, we got a big vein of quartz over here. That's going to be left behind, because nothing really dissolves quartz. It's going to be broken smaller and smaller and worn down and rounded, but it's not going to chemically go anywhere. It's going to be moved. And so we're going to get it making up the majority of beach sands in the world. So this indicates we could be very far from the source, that we're only left behind with quartz. Nothing else is left. We're not getting any feldspar in here. You can. There's plenty of sands that would be an arkose that are made up of mostly feldspar, indicating not as much transportation from the source. But all quartz, that means we're pretty far away from the source, unless we have a monomineralic source. And that means that if we have a mountain made of quartzite, which is metamorphosed sandstone, it's all quartz. So if we wear that down, the sand right at the base of the mountain is still going to be pure quartz. But texture should be different, because you should have chunks of pure quartzite, and you are looking at texture and composition at the same time. And finally, one of my favorite sands, and any place that has the nice, beautiful white sand beaches that we enjoy, like the Bahamas, and this is from Florida, is going to be something completely different. Okay, so we're just talking about siliciclastics and how maturity changes from the source to all this transportation, all this erosion, and creating very fine sand, often very far away from where that source is. Well, in this case, the source is not from land. We're looking at little seashells. The white sand that everyone enjoys is made up of dead animals, basically. It's fine. I mean, that's what we have in the oceans there, and makes them very special places. But I even have a few little shells, because not everything is broken up here. Got a nice little, looks like a coquina shell. This is a biological sediment. It's not from land. It's from reefs and other very biologically rich environments just off the coast. The waves wash this stuff up, break it up, toss it around, and it's dumped right there, creating our nice white sand beaches. So I think just understanding the source of sand and the geology of the area and where that sand's coming from and the processes that it had undergone before it makes it to the beach that you're walking barefoot on is a very special story in sedimentary rocks, and it's kind of the nuts and bolts of sedimentary rocks. If this makes sense to you, you're in pretty good shape, because it's combining textural maturity, mineralogical maturity, all sorts of stuff. It's very cool. Now, one thing I do want to mention is a common misconception that I've noticed is people tend to think that this tells us how young or how old the sediment is. It doesn't. This Hawaii sand is not necessarily younger than the North Carolina sand. This is not how we date rocks, okay? This is not how we date sediments. This is only telling us the extent of transportation and the distance from the source, and quite a bit about what that source may have been. This isn't telling us how long ago that sediment was eroded or anything like that. So we're not looking at age here. We're not looking at age for these rocks. Okay, and so anyway, much of this stuff with the different minerals is pretty much slide 13. Is kind of a big picture that says a million words type of slide. So a very good one. Okay, now we're getting on to sedimentary structures. So that loose sediment, as it's becoming a sedimentary rock, and before it's becoming a sedimentary rock, is undergoing a current. Wind, water are pushing it around. That current can change. So we may go from a very, kind of a calmer environment where we're getting very fine grain. Actually, I don't know which way this was. That's why you want to record that stuff when you pick up a rock from out in the field, because I have no idea which direction this was. But anyway, we have fine grains down here, big grains at the top. This is something called graded bedding, and this indicates that the current, probably water in this case, because we have some pretty decent-sized sand grains and pebbles here. Wind probably isn't going to move stuff like that. We're looking at water. That water current changed. It went from slow, it picked up speed. We could see graded beds that are repeated over and over and over again, telling us about the energy level of that system while that sediment was being deposited. So pretty cool stuff. So graded bedding is a very special type of sedimentary structure. It tells us a whole lot. I've got some really great ones here though. The next one I want to talk about are ripple marks. Ripple marks are things that we probably see in creeks, we probably see along muddy shores of lakes. It's something that we're kind of accustomed to seeing. But the cool thing is just like the sediment itself, they can also solidify and form a hard, solid rock. They can be preserved, like dinosaur footprints or other remnants of a disturbance that happened in that sediment. They can be preserved. So I have some neat ripple marks here. Ripple marks can tell us a couple things. In this case, and we may have some still pictures if we're not able to focus too much, but the ripples are leaning. They look like they're leaning from the right to the, it looks like they're leaning toward the left. This means that the current was moving this direction, okay? Because we are going to be steeper on the leeward face, the side facing away from wind or water, than we are on the stoss side, the side that's actually facing into the wind or the water. So as the current is moving this way, it's making these little ripples that are asymmetrical. That tells us the current was going in one direction. Now what's special, and that could be many places by the way. This could be a river, this could be windblown because of how fine these grains are. This is probably windblown, but I have no idea where this rock actually came from. But what's really special, what really pinpoints specific environment of deposition is when those, this is probably better side, when those ripple marks are symmetrical, meaning that if you draw a line straight through one of them, it's pretty much equal on one side as the other. This means the current changed direction, and that's very special because that indicates that doesn't happen in many places. That can happen in tidal places, so as the waves or the tide goes in and out, or as waves themselves on a much smaller scale go in and out. So we have current changing constantly, and that can point to a tidal flat. So we look for symmetrical ripple marks when we, are thinking something might be a tidal flat. If we're getting asymmetrical ripple marks, it's probably a slightly different environment. So very little details, but they're preserved in sedimentary rocks. That's very special. Probably the best, and not to be objective or anything, but it probably is the best type of sedimentary structure is cross-bedding, and that's because it's so informative. So this one is from Utah, from Checkerboard Mesa, the Navajo Sandstone out there in Utah, I believe Arizona, Colorado. It shows up in a few places. It's windblown sediment. This was from an ancient desert during the time of the dinosaurs, and shows us, I know that, because the range of grain size here is very narrow. They're all pretty much about the same size of grains. We're not getting any slightly larger or smaller grains of sand. They're all about the same. And that usually points to windblown sediment. There are other factors. So we have the wind is going to move the current, the current's going to be moving in different directions. And as it's doing that, ripple marks may occur along the surface, and we do have some here, but especially along the side, we're going to be getting cross beds. So basically each dune that forms, each little dune migrates over time, over time, over time. I'll have a link to a video that you could see an animation of how dune migration occurs and how these cross beds form. And they actually point to the direction of wind blown sediment. So that's a lot of information, and if we're looking at the Navajo Sandstone, which is Jurassic, we can actually tell the dominant wind direction during the time of the dinosaurs, which is very cool. And it's one of those things that people ask, well, how did you know that? No one was here to see it. No one was there to see it, Well, sedimentary rocks are a great record of that, right? If being a geologist, perhaps particularly a sedimentary geologist, is like being a detective, these are our clues, So we're looking at modern day environments where these sort of things happen in order to determine what would have happened 180 million years ago, 200, however long ago. Okay, and then a very cool one here, a very unusual one, is something called mud cracks. We've seen mud cracks, here in Kentucky, like at a park or something where you have a muddy area, and because clay, we're back to clay, because clay contracts when it dries and swells when it's wet, we get cracks forming during pretty dry times. Well, just like things like raindrop impressions or burrows left behind by worms, or ripple marks, or any of these other things, they can be preserved too, which is very special. So we can kind of see these big kind of polygonal shapes here. It's not terribly clear because, I mean, it's a rock. It's not nearly as clear as you would see, happening today. But these are mud cracks, telling us that, this could be from a humid environment. It could be from a pretty dry environment. I don't really know. But one thing it does tell us is this was not deposited in the ocean. And since most environments of deposition are marine, or especially shallow marine and coastal, this, the fact that we know that this was a terrestrially deposited sediment is special. This was on land when it was deposited. A lot of these others, they could have been into the ocean. So anyway, that's kind of an overview of we're creating sediment in the first place through a lot of different processes. We're doing things to that sediment through the processes of erosion and transportation. As it's finally being deposited and laid down, we are getting different textures and different sedimentary structures forming that tell us very special things about that particular environment in which that sediment found itself. So, and of course, going back to our local limestone and the coal and the sandstone, over time, we're seeing how these sedimentary rocks can tell us about the changing of habitats, and that's a very cool story too. So, sedimentary rocks, no one was there to see them form, but they tell us so much about the history of the Earth, or at least the surface of our planet. All right, that's it.